Yeah, I started recording. Okay, yeah, good. Then let me share the slides. Okay. So yeah. Anyway, just recap. Let's start. Yeah, in the last class uh, yeah, we are discussing about the concept of a process, and so on. Uh, and then we are discussing about schedulers because you have multiple processes that are present in the memory, so they are ready for execution. So therefore, you have only one processor. So therefore, we need to schedule the processes to the CPU so that always CPU has some process to execute. And there are basically there are two types of schedulers can be observed in the system. One will be the long-term scheduler, other will be the short-term scheduler. And the short-term scheduler is related to the scheduling the process to the CPU, where so that whenever the CPU switches or whenever the CPU suspends some process because of interrupt or whatever the reasons, so then the next process will be scheduled to be executed by the CPU. So for that purpose, the short-term scheduler will be there. And yeah, as you see that it selects the process, which process to be executed next. And there is another scheduler known to be the long-term scheduler. So this will be on the secondary memory. So it means that the processes are created, but they are still in the disk. They are waiting for time to load into the main memory and all. So this is also known to be a long-term scheduler because the terms here the long-term, short-term, because the short-term means here the CPU scheduler or the long short-term scheduler, it need to make a decision, scheduling decision very frequently because the process when it executes by the executed by CPU and all, so it needs IO, then it suspends and the next process to be executed, or otherwise because of the time slots, because of multitasking environment, where the time slot will be expired, so that even though the process can execute some more time, but still it has to be stopped and next process to be given. So that way, the short-term scheduler very frequently it schedules the process. So it means it has to take a decisions very fast. Whereas other way, the long-term scheduler, where it will take a decision or its functionality will be encounters at a longer intervals because here the job of long-term scheduler will be it has to schedule the process to be loaded into the main memory as and when there is a room for availability there and all. So that way, this is not a long-term scheduler. And while doing that, the long-term scheduler will have enough time to make a decision. So therefore, it also look at the nature of a process. Based on that, to balance the activities like a kind of resource allocation, efficiency of different resources and allocation of resources and all, it just properly feed the appropriate process to the main memory and all. Hmm. And in some say cases where there will be only one scheduler will be there, like only the short-term scheduler will be there. There won't be any long-term scheduler. Hmm. And here the details of the same thing, like as I mentioned here, the short-term scheduler very frequently its action will be there because it has to schedule the process to the CPU. And based on the time quantum, every time the CPU switches the process, that is one way. Or other way also, based on the IO requirement, the process itself will be suspended, right, to take in IO. And the long-term scheduler will invoke very frequently, right? And as I mentioned here, the long-term scheduler controls the degree of multi-programming, right? That depending upon the number of processes that are there in the memory, it just sometimes it loads into the main memory, And the nature of a process I have mentioned here, the nature of process, the depending upon the process nature, whether is it like a process is involves lot of computations or a process that is involves lot of IO operations and all. So based on that, you can say the process are either IO bound process or a CPU bound process. So here IO bound process means that particular process is mostly involved with the IO computation. That means inputting a data and again outputting the data. And so that if the nature of a process is like that, it's known to be like IO process. And if the nature of a process is mostly of computationally involved, like for example, a lot of time it needs the CPU most of the times, like just involving computations, like for example, computing, for example, as you know, the factorials of a bigger numbers, or computing the, for example, the to decide whether number is a prime or not. So likewise, all these things, they involve a lot of computations and all, right? So that way, a process can be viewed as either a CPU bound process or IO bound process. And some processes are balanced. They have both IO and CPU, but it's not like not too much of bias towards either CPU or IO bound. So that way, the processes are basically viewed as CPU bound and IO bound process. So while in the case of long-term scheduler, when it makes a decision, it will see that what are the processes that are there in the main memory. If the majority of them are the CPU bound process, for example, then the device queues are empty, device queues are vacant, the devices are not properly utilized, other resources and all. So therefore, it tries to feed the IO bound process. Whereas other way, suppose if the most of the process or majority are IO process, so in that case, to make the CPU to be like effective, more effective, or to be more efficient, so it tries to feed the CPU bound process so that it balances the nature of a process in the main memory, so that all resources are utilized very effectively. Otherwise, it will be biased. Suppose if there are more of CPU bound process, the CPU will be utilized effectively, fine, but the other devices or other resources are not utilized effectively, right? The other way, if it is IO bound process, then the CPU will be not effectively utilized, and most of the times, most of the processes are in the IO queues. And there is another scheduler that will be there in some systems. This is known to be medium-term scheduling. Here, the job of this medium-term scheduler is that it tries to sometimes, actually, depending on the requirements and all, it tries to like swap out some of the partially executed process onto the disk. And after some time, again, it will be swapped into the partially executed process into the main memory and all. So that this is for various reasons. This will be carried out for controlling the degree of multiprogramming, and sometimes if there are more number of processes in the main memory, so in that case, the process that have the lower priority and other cases, other things where they will get a very less time or very less frequently they will visit the CPU and all. So for that, to take care of those activities and all those things, so here what it will do is that sometimes a process that is partially executed, it is just swap out and push it into the disk, secondary memory. And after some time, then again it will be swapped in, and then it starts executing from wherever it is left over. So that way, this is known to be medium-term scheduling, and it basically the swap out the partially executed process from the main memory to secondary memory, and then again swap in and starts executing. So these are the different types of schedulers that are used in generic.
Excuse me, sir, I was having a doubt. May I ask?
Hello?
Hello, sir, I was having a
Hi.
doubt. May I ask now?
Hello?
Hello.
Yeah, tell me.
So in the previous slide, like you said that we retrieve a partially executed process from the
Uh,
secondary memory.
Correct,
So
correct, correct.
isn't that access costly? Like instead of accessing partial from the secondary state, I can probably compute it directly in less time.
No, 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 not this one, not this specific process. Actually, here, this is not that easy and all. Just I made it in a very simplified fashion. No, what I'm saying is that sometimes there is a need that for the sake of overall activity to be beneficial, sometimes even the partially executed process also will be shifted from main memory to the secondary memory, and then again brought back, and then it will execute from later on. Because yeah, as I understand from the specific process point of view and all, it is delayed because moving to the secondary memory and again back from that. But from the overall perspective, sometimes there is a need arises that at that time it even the it means that actually it's a rare thing to happen actually. So there is a need that arises that there is some process that are very badly affected. They are very much starving for getting a CPU and other things and also in that case, they will take out some of the process completely from a main memory and push it into the disk. And then after some time, they will be brought back. So that job will be carried out by the medium term scheduler, I'm saying. So in that effect, this particular specific process may be affected, but on the whole, the efficiency or the overall the performance is may be improved. That's the idea. Okay. Yeah, the next thing that we are going to discuss here is the process creation, and well, the later on again the process termination and so on. This is one very important topic where all the process, whatever we are saying, the execution of process and all. So those are created by this one by using the uh, process creation, and then afterwards they will be the moment the process is created, then afterwards it will be loaded into main memory for its execution. Then upon termination, again the process will be removed from the main memory as well as from the kernel table and all, process table and so on. So that way we'll now we'll discuss about this one process creation, termination, and so on. And after that, the next topic to be discussed after this will be the process communication, inter-process communication, right? So yeah, let us start with this, the process creation. And so we know that yeah, we have seen very briefly at the in the very introductory chapter and all. There are some system calls that are used for creating a process and for terminating a process and so on. So here we'll go a bit more details about that. So there is a need for process creation that all of us we know that because if you take a very simpler example, in case of a client server model, a client server application, you have a server process and we have several clients are there, right? Assuming that the server process is a web client, web server, for example, and you have several client processes are there, and each client want to connect to the web server for fetching some of the web content. So that way there are several clients, they want to access the server. So in that case, you have a server process will be there. And suppose if the server process want to service all these clients, then it has to go by like all these client requests, they have to be placed in the queue or in the some fashion, and then it has to address one after another and all, right? So for this way, if you want to address all these clients one after another and all, then it takes a lot of time because there are huge number of requests used to be there, and it will be very difficult to manage by the process server single server process and all. So that the other alternative is that server process can create a child process. One way is that server process can create a child process. So whenever there is a request from a client, it creates a child process, and then the child process will be assigned, or child process will take up the request of this particular client. And again, the server, the parent server process, whatever is there, that is again waiting for the client request. So whenever the request arrives at that time, the server will spawn a new child, and then that child process will take care about the request and all. And again, the server will go back to like in the waiting state for the request and all. So this is one of the examples. And not only that, there are in the next slide, you can able to see that the different applications of that. So that way, that means here there is a need for creating a process and all. And not only that, even for in a system to to run the user applications and all the user applications will be in the form of somehow, some or other way, we have to create a process, and in that process, the user program will be run, right? So therefore, here, first of all, how to create a process, that by using a system call, you can do that. I will see that with respect to the Unix operating system, a fork system call used to create a new process and all, right? And then afterwards, suppose the new process has to be again will be different from a parent process. Then by using the another system call known to be exec system call, we will replace the parent, will replace the parent process with the new process, whatever is required. So first of all, let us see that when a process is created, the created process is known to be child process, right? And the process which is created, it's known to be parent process. So that is the relation between a parent and a child process. A process that is created is known to be a child process, and whichever is creating that one, it's known to be parent process and all, right? So initially the child is a duplicate of a parent. So what it means is that, so whatever the parent process is there, it's exact replicate of the parent process will be the child process and all, but in a different the address. Because for suppose the parent process is there from 1000 to 1500 kilobytes, for example. If it creates a child process, then the child process size is also 500 kilobytes, but it will be in a different address space, like from, for example, 200 to 2500 kilobytes. So the same address, that means the same size, same thing, everything will be copied into that. And so that way the child becomes a duplicate of a parent when it's just created and all. And after that, a child process, a child has a program to be loaded. That depends on the requirement. A child process can run as a parent. Suppose, as I told the example, like in case of client server paradigm, the server can prawn the child, and the server will that is nothing but whatever the server process is there, the same process will be replicated to the child, and the child will take care about the request from the client. So likewise, in that paradigm, the server will be the process, whatever is created by the server process, the parent process, the childs also remain same as the parent process, exact replica of a parent process and all. But sometimes if you want to load, if you want to run a new program, so in that case, after a child process is created, initially when the child process is created, it is a duplicate of a parent. Then after that, if you want to run a new program into that, or a new activity into that, then by using this exec system call, after a fork, it will replace the process memory with a new program and all, with a new program. So that way, for example, in your command prompt and all, you are giving different commands and all. So whenever you are giving a command, first initially it will just create a child process. Then afterwards, whatever the command, in that command, whatever the code used to be there, that code will be loaded into that particular child process. Then the child process runs as per the new program, whatever is there. So that way, first you can say in the creation of a process, first the child process will be duplicate of a parent. Then afterwards, depending on the requirement, suppose you want to run a new program in that process, then by using the exec system call, you replace the process memory with the whatever the desired new program is supposed to run. Right. So these are the two system calls that are used in case of Unix system for creating a child process, and the child process has to be replaced with the desired process center. Right. Yeah, right. So you can see here, this is the overall flow of the process, the parent and child relationships and all. So by using a fork system call, a process creates a new process. So here the fork system call, and here is executed by a parent process, and then a child is created. Child is created. You can see here child is created, and at the same time the parent also will be there. Parent also there, and then the child. After the fork execution, you have two process. One is the original process, and other one is the new process. And in that new process, suppose if you want to load some other program into that, Then immediately after the fork system call, the exit system call will be run, will be executed. And in this through exit system call, so whatever the program that need to be loaded, so it will be loaded into the child process, loaded to child process. Then the child process becomes a separate process, a new process. Otherwise, it's a replica of a parent process, right? Then after the exit system call, then the child process will be a new process. It's that nothing but a new program will be there embedded into that, and those statements will be executed and all. And then upon completion of the child process, sorry, can you see the slides? Hello?
Yes, sir.
Yes,
Yes.
Hello?
sir. Sir.
Yeah, yeah. Somehow I just 1 minute. Yeah, right. Okay. Yeah. Yeah, right. So here there are two processes. One is the child process and the parent process. And the child process that depending on the requirement, if it want to run a new program, then by using this exit system call, it replaces its process map the memory with the new program, and then that program will be run. And then at the end of the program, that program will be terminated by using the exit system call. This is exit system call. It terminates. And here upon the process, the parent and child, they have the different relationships. In some cases where that depending on the requirements and all, the parent upon creating a child, it just wait for the child's completion. It wait for the child process completion. So here, this is the scenario where, in this case, where the parent, upon invoking the fork system call, a new child will be created, and then a child process will be run. And upon completion of the child process, then the parent starts executing. So for this purpose here, upon executing the fork system call, the parent will invoke the wait system call, and this wait system call will be activated only upon completion of a parent child, upon a child process. So upon the child's completion, then the child it returns the status signal to the wait, and with that wait, it will return from the wait system call, and then the parent starts executing and all. So this is one way of doing that. And whereas in some of the cases, some of other applications, the parent need not wait. The parent will execute its own way, the other parallelly. So that way, there are different ways. This is one of the ways where the parent, upon creating a child, it just wait for the child's process to complete, and the output from the parent upon child's completion, then it starts its execution. Yeah, now you see that now this program here, this is a very simple program. This just illustrates that how the parent-child process will coordinate or will run concurrently on the system and all. And here you can say that yeah, here this is the process as we already known that each process has some process ID, right? And then here, this is the main program, and or you can say that it's a program. And in this program, you say that here at this point, we invoked the fork system call, like fork system call, and then it's nothing but equal to some PID. It means that the fork system call will returns the process ID, will returns some integer value, because the process ID is nothing but it's an integer value. The process ID is an integer value. So therefore, the fork system call, it won't expect any arguments, but it returns some integer value. It returns an integer value that is captured by PID. And now here upon the fork system call, till the fork system call, there is only one process. And then once the fork system call is executed, now there will be two processes will be there. One is the original process, and the other one is the newly created process. So there are two processes will be there after the fork system call. And then for each of these two processes, they start its execution after immediately upon the after this fork system call. It means that suppose whether it may be child process or the parent process. So both the process upon execution of the fork system call, the execution starts after that, immediately after this. At the fork Even the parent also, the parent starts from here anyway. Even the child also, the control starts from, or you can say that the process, this one, what is that, in the CPU register, what is that register name? One of that which used to points to the next instruction to be executed.
Program counter.
Yeah, program counter. Yeah, the program counter in the even the child process also will be start from here and out. So it means that after the fork system call, then both parent and child starts from this point. And now here, because the fork system call returns returns some integer value, right? And suppose if it returns a negative integer, it indicates that the fork is failed. That means there is some problem with forking a child, the forking process itself. So that will be this particular if statement, and here these two statements will take care of that. If there is any error in the execution of fork system, then it will be displayed like this. Or otherwise, if the PID equals to 0, yeah, as I mentioned here, this is a very settle point here, very important point here. Upon execution of fork system call, I mentioned that after this there will be two processes. One is the original process, other one is the child process. And here upon execution of this fork system call here, this fork system call will return the process ID of a child process, whatever the process ID that is given by the operating system. So that will be returned to the parent process. Whereas for the child process, it returns 0. Whereas for child process, the fork system call return to 0. Whereas for a parent process, the fork system call return the process ID of the child process. So that way, other than that, the entire code remains same. The entire code remains same except this process ID, PID, whatever is written by the fork system call. For a parent process, it returns the process ID of a child process, whatever is newly created. And whereas for child process, it returns the 0 because from here, because the entire code remains same. So the fork system call returns the process ID of a child to the parent process. And whereas for a child process, it returns a 0 and all. So based on that, you can able to distinguish, you can able to say that whether the parent process is running or whether the like a child process is running and all. So for that here, you can see here after this, after checking that whether the fork is successful or not, right? The next statement to be executed will be here. If PID equals to 0, it means it's a child process. If PID equals to 0, then execute this one. And here in this case, what happens is that the child process want to run some other program. So therefore here, after we are checking that if the PID equals to 0, it means it's in the child process now, then perform this. That means that exec system call, whatever is there, exec system call, it will load the ls, that's the command here ls. That is this again a process. That means if you want to know the what are the list of files that are there in the directory and all. So that way this is bin ls and all. Then that means that it is loading the corresponding the program and all here. That is a new program that will be loading into the child process and all. Right. And yeah, if it is, yeah, if it wants to run a new program and all. Otherwise, actually there won't be any Excel and all. Just it will be the PID equals to 0, it will be there. And then here, after doing this, that it means that now we are loading the new program here. Then that new program will be executed, right? Then afterwards, then the new program will be, it completes because there is no other, the PID equals to 0. So therefore, the child process will load the new program and it executes. And then at the end of the execution, it terminates. It terminates. Then here you can see that here, because you see that there is a program, the same program will be there in the both the parent and child and all. So to distinguish between the parent and child, only the PID will be used for loading the new program into the child. So here the PID equals 0, then they load the new program and it will be executed. And else, if you want to run the parent program, then you are running the parent program here. That else means here PID is equals to not equals to 0 because PID is the error case is already checked here, less than 0. It's less than 0. And then if the PID equals to 0, then the child process. And other than PID equals to 0, it will be a parent process because here it returns the integer, usually the process ID of the child process. So with that, now the parent process will be run here. So now here the parent process, as I mentioned that the parent process, that depending upon the requirement, sometimes the parent process wait till the child completion and all. So here in this case, it's doing the same thing. So in the parent process, now what it is doing, just wait for completion, child completion and all. So whenever the child is completed, right, executing the last statement and all, exit and all, then the child process returns the status value to the this wait system call. So that way the parent will come to know that yeah, the child has been completed. And then suppose, and if there is any further statement, then the parent will run. Otherwise, it returns and all. Right. So that way here you can see that the PID by using a PID you can able to discriminate whether it's a whether you are running the child process or the parent process and all. And so here this way by using this except system call, you can able to overwrite the child's process of the on the desired the new process and all. Otherwise, the child process will be exactly the same code and the same replica of the parent process. That also requires for certain applications, as I mentioned, in case of a client server paradigm where you have multiple requests are there and a single client may not, single server process may not handle those things. So therefore, you use the like spawn the new childs and where the childs are happens to be exact replica of a parent process and all. So that way you can have the parent and child can coordinate and they can able to run concurrently by the CPU and all. And yeah, this is what here you can able to see here. This is a fork system call. The parent and the both child will be there. And then the child, if it wants to run the new program, then by using exit system call, the desired program will be loaded into the child, the process memory, and that particular program will be run. And upon completion of that, it returns. It returns. Then the parent may be waiting for the child completion. Then upon returning from the child process, the child termination, then the parent will resume and then it starts its execution. Right. And this is the way the processes are created. Like this is an example for an operating system Solaris, where you can able to see that you can see initially there is that depends on the different operating systems more or less, but the idea remains same. Here this is starts with the PID 0, process ID 0, and then it initially creates different process, the init process whose process ID equals to 1, and with this init process it further create a process for the user applications or for user process, and whereas these two are related to the kernel process that is related to the operating system. So this is related to page out, and this is nothing but maintaining the page tables and the memory management purpose. This process further will be used, and this is like a file system management and all these particular process. Further later on, further process will be created through this, and this init process is used to create further process for the user request. So here in this case, you can see this particular branch where it used to create a process over the internet using Netscape and the other things. Whereas here under user process, where here it creates finally the user process like ls, cat, and other things and all. So that way, the process, any new process it want to create, it want to run and all, so it has to be created, and then once the process is created means then it will be loaded into the main memory and it will be executed and all. So this is the way the process will be created from one to another and all, right? So and then by using this relationship, the parent knows the child's the process ID. So likewise, by knowing the process IDs, you can trace back and you can able to track the overall the structure of the these parent-child relationships and all.
So,
Yeah.
so when a child process is created like in Netscape, so what will happen to the PID? PID 0 is already scheduled to this S
Yeah, yeah.
cache.
Correct. So all these the PIDs, whatever here, they are unique as long as that may be like 4-digit or 5-digit number or whatever. All these are unique and all. All are unique. All PIDs are unique. And basically using the PIDs, the kernel maintains a table, and also with that it comes to know about it. It maintains the information related to what are the active process and all those things will be maintained by the with respect to the PID and all. So therefore, this PID is an attribute of a process in the process control block also, right? And it need not be the PID of Netscape is always not this way, right? It may be different also. It's not like the port numbers or the process IDs. It's not that port number specific to that one, right? It may be different, right? So these
Sir,
are the various ways you can create the PIDs.
sir,
Yeah.
sir, if the Netscape tries to create a child process, what will the PID of that child process?
Not that will be the different. That means through Netscape, that means you are using Netscape as a user. You want to use the Netscape for some browsing something or something like that, right? So then it creates a process. It creates a child process, right? And then that child process, whatever the request your request is, that request will be processed. That request will be used, will be executed and all. Like the Emacs is suppose is an editor, for example. It's a process, right? And then when you are using the Emacs editor, when you open the Emacs editor with the different files, it just creates a different process IDs. And then it runs, and each of them will be run like separately that way. Like command shell, for example, CSH and all. So you have this is again, this is a process, and then it creates, if you want to run on CSH, if you want to run some other program, some of your executable file, then that executable file will be assigned a new process and all, right? So that way it generates the process, each process, whatever need to be run. So that is to be, first of all, it has to be created. When it creates, it becomes a duplicate first, and afterwards a new process to be loaded into that. A new program is to be loaded, and that will be executed. Right? Yeah. Now the coming to the termination of a process, and here the process termination is nothing but there are two ways the process will be terminated. So one is the normal termination. It means that when the process is executing, process is nothing but a sequence of instructions. They are executing one after another. When you reach the last statement of your program, then either the user will write the last statement as exit, or otherwise he will put simply the return and all, return 0 or whatever. And then the compiler will when it compiles, then it inserts the exit statement so that the program will be completed. The program is terminated normally. When it reaches to the last instruction and it terminates, it's a normal way of terminating a process and all. The other way is that actually a parent can terminate the process. A parent can terminate a child process and all. So because of different reasons and all. So we'll see here later and all. Here you can say that a process executes the last statement and then the system delete it. So at the time of termination, the process, each process has to convey or has to return the status information to its parent and all. And that will be done by using a wait system call, because the parent is will be waiting with the wait system call, and then that wait system call will be again revoked from the status information that is provided by the child and all. So that way the output data from a child to the parent is through the wait system call. That is, the parent is invoking the wait system call, and then whenever the child completes this process, then it returns the status information. Again, the status, as I mentioned, like the status will be like a non-zero status that indicates that the process is terminated properly in a normal way completely. And whereas if the status is negative, that indicates that the process has been terminated abnormally because of as the parent might be terminated and all. It's not a forced termination. It's not the normal termination. So the process, then upon the terminating the process or upon completion of a process, the process resources, whatever is there, that will be deallocated by the operating system, and then it will be used by some other process. And then as I mentioned, there are two ways of termination. One is a normal termination, that is like reaching to the last statement of execution, and then afterwards its completion. And the other way is that the parent can terminate the execution of a child process because of various reasons. One is that child has exceeded the allocated resources. Yeah, as I mentioned, one more thing, when a parent creates a process, the resources whatever the parent has, and those resources also shared by the child. That depends upon the different operating system. Sometimes whatever the resources the parent has, all the resources will be shared by the have the rights to has a right to a child has a right to share use those resources and all. And sometimes no, the parent will specify a limited set of resources for each of the child and all. So likewise, the child can use the resources of the parent partially or completely, or even not also, because when the child process is loaded with a new program, so in that case there is nothing, no, there is no need of the child process to use the resources of a parent and all. So that way, the child and parent can share the resources, depending on the requirement and all. And yeah, and here the process can terminate. The parent can terminate a process, child process, when if the child exceeded the allocated resources. Suppose whatever the resource allocated, if it crosses the threshold or beyond that, then the parent can terminate the child process. And the second one is that the task assigned to the child is no longer required, for example. So in that case also the parent can terminate the child process, because the task is no more required. Before that itself it might have interrupted, or some other signal might have received. So in that case the purpose of child is no more required. Then also the parent can stop or terminate the child process forcefully. And then another case is that suppose if the parent is exiting, suppose the parent is terminating or parent is completing, for example. So at that time, the operating systems will not allow its child to continue. So operating system will not allow child to continue. In that case, so whenever the parent terminates, before that, all its childs will be terminated. So this process is known to be a cascading termination and all. Like you have a process and it creates a child, and the child creates other childs and so on. And if a parent somehow it want to terminate, or by whatever malfunction or whatever forcefully it has to terminate, for example, in that case, whatever the childs that are connected to that particular parent process, so all has to be terminated. And that will be carried out by the operating system. And this is known to be cascading termination and all. And in that, related to this termination itself, there are two other things, zombie and orphan process. And a zombie process is nothing but, so as we know that in general, a child process upon its termination, it has to return the status of its termination to the parent, to the parent. And how it will return to that one? It return to the statement, because the parent is waiting, parent is invoking a wait system call to accept this the status information, the termination status. Suppose, for example, if a child process is completed, but it want to return the status information, but the parent is not invoke the wait system call. Parent is not waiting. So in that case, that particular transition state where the child process has completed, it come to the last statement and it has completed, right? And then, but it want to return the status, but for returning the status, the parent is not waiting for that, right? So in that case, in that particular transition state, the process are known to be a zombie process, where it means that in principle the process is terminated, but still it lies in the operating system, the process table, still the process is present because it want to return the status to its parent process. So those processes are known to be a zombie process, where they are in the transition state. They are terminated, but still their process ID and some other detailed status information is still present in the process table maintained by the kernel and all. So that those are known to be a zombie process, right? And there is other process known to be orphan process. So these are also something related to that. It's the orphan process are nothing but a process. You have a process, and each process is connected in the form of like a parent child in the form of a tree and all. Suppose, for example, a child process is there, and when the child process completes, our child process is there, but a parent process somehow it was terminated. It has completed. Somehow the parent process is terminated without terminating its child process. Then the child process becomes known to be the orphan process and all. Where in case of a zombie process, A parent process will be there, but the parent process is not executing or not invoking the wait system call. So therefore, the child process, which are they have completed, but they are not able to return the status. So that way they are the zombie process, whereas orphan process are nothing but a parent process will terminate without terminating the child process. So then the child process becomes, they are not connected to the tree. So they becomes orphan process. So in that case, there is alternative, like if suppose for example, if a parent is terminated without taking care about the child process, for example. So all these childs will be connected to the init process, because the init process is the topmost process of all the user process and all. So whenever this kind of process becomes the orphan process, then those processes will be connected to, or they will become the child of the init process. So that way, the later this child process, they will return the status to the init process and all. Right. The same way the zombie process also. Like for example, if the parent is not at all issued and wait system call and all, then they become a zombie process, but they will not present for a long time. So in that case, suppose if in that case there is a init process, as I mentioned at the upper portion of the tree and all, it used to periodically generates the wait system call and all. It periodically invokes the wait system call. And at that time, in that wait system call, for that wait system call, whatever this kind of a zombie process or orphan process are there, so they will be taken care by that init process and all. It means that whenever the init process, it periodically invoke the wait system call, at that time, if there are any zombie process over there, and those process will return the kernel will return the status of the zombie process to the init process. And then once they are informed to the next level, then the zombie process can be disappeared. They can be removed from the process table. And anyway, the orphan process will become a child of that init process, and it will execute if it needs to be executed later on. So that way the process will be taken care. So this is the more or less the way the process will be created and terminated and all. Yeah. Then we'll come back to the last topic of this related to process. That's not to be inter-process communication. And here the concept of inter-process communication will come into the picture if the processes are cooperating or if the processes are dependent. So basically the process, you can view them as a dependent or independent, dependent and independent, right? Or you can say that dependent means a process depend for its execution. It depends on some other process. A process for its execution or for its execution, it depends on other process. Or you can say that a process, you can say here the process can affect or to be affected by the other process, are known to be a cooperating process or dependent process. Or otherwise, the independent process are nothing but the process is not not affected by the other process. It means it's purely independent. The particular process will not have any relation or any like information exchange, anything, any dependency with other process and all. So that is as simple as that. That's not to be independent process. And the other process are known to be cooperating process or a dependent process. So the cooperating process are nothing but those processes, either they affect the other process or they are affected by the other process. So that is a very straightforward way of defining this one, cooperating process. And why you require this cooperative process? So you require cooperative process with several reasons. One is that information sharing. It means that there are occasions where you have multiple processes share the information. Like for example, you have a database and the database has to be shared or be utilized by the multiple processes and all. So at that time, you need to create an environment such a way that whatever the data that need to be shared or whatever the file that need to be shared has to be shared across the process without any inconsistency, without any issue at all. So that means you need to provide an environment where the multiple process can access a same shared entity or shared file or whatever. So that means that there is a need for the information there is a need for the exchange of information between the process. and sometimes the communication speed up. Hello? Yeah. Yeah. Right. So any question, somebody? Yeah. Okay. Then the other things are like you see that the communication speed up. Communication speed up means suppose we have instead of having a process, a lengthy process and all, you can split that process into the multiple process and where you can coordinate among these processes so that you can increase the speed up also. That means you can reduce the execution time and all. If you can break up the process into multiple process and you have like for example multi-processor systems are there, then you can allocate these the sub process or the multiple process onto the different cores and you can speed up also. And likewise the modularity. And so sometimes actually you have now have an application having huge process instead of having single process. You can have split that into a process with the different modularities, and where you can able to link up the this process by arranging them in a proper hierarchy. You can have perform the overall job, right? Okay. Yeah. Hello. Yeah. Anybody? Right. Okay. So that way there are different situations where you need to have a communication between the processes required and all. Not only that, wherever most of the times, very rarely the process has to be have to be independent and all. Always there should be a communication between the process. Either the user process will communicate with the operating process or either way. And all. Very rarely the process will be independent, right? Most of the times, as you are saying, even in the normal simple C programs also, you need to have some input you had to capture from somewhere and all. And for that purpose, you had to make use of the operating system process and all, right? So that way, there will be a need of process to process communication is required. And that will be carried out here by using the inter-process communication. Okay. Yeah, this is what mean by the term inter-process communication. And to perform this inter-process communication, there are two different modes of inter-process communication. One is the shared memory approach and other one is the message passing approach. So we'll see the details of this. Yeah, here yeah, these two diagrams showing that here the diagram A, here it shows that the inter-process communication by using message passing approach, and the B here is nothing but the inter-process communication through a shared memory approach and all. So first let us look at the shared memory approach. So in case of shared memory approach, the idea here is that you know that this is the overall memory and here the kernel will be there here and then the remaining portion will be given for different process and all. So in case of shared memory, the idea here is that a part of a memory segment will be made it as a shared memory segment, and that particular shared memory segment will be accessed by the multiple process. Accessed by a multiple process. So in general, as you know that the process is allowed to access its own address space. It cannot access the address space other than other than its own address space, because that way the operating system will protect the other process, will control the process from each other and all, right? So that's the in generic way where each process can be allowed to access only its content, only its memory map, only its memory allowed memory segment and all. Whereas here in case of shared memory, we are deviating from that. In case of shared memory, we'll declare a particular memory segment as the a shared memory segment. And then for these shared memory segments, the process will access to the shared memory segment. That was suppose, for example, A and B want to communicate, for example. So in that case, the process A will be attached to this particular shared segment, and the process B also will attach to this particular shared segment. Now, after that, now the process A can able to access the shared memory segment the normal way, the way it accesses its memory content, normal memory addresses. Like the same way, the process B also now have a right to access the shared memory content. Otherwise, in general, where the process A means it's allowed to access the memory only in its region. Here, this particular region is the process A. So in a normal circumstances, this process A can able to access the memory only in this range, right? Similarly, process B only in this range. And now here to perform the inter-process communication using a shared memory concept, the idea is that you take a segment of memory which is declared as a shared memory segment. For doing that, we use the operating system call, right? For making the segment to be shared segment. And afterwards, again, a process A want to access the shared memory. Again, there is a system call. So with that, the process A can able to attach to this shared memory. Then in that case, then what happens? The process A's memory will be starts from here to till this particular one. That means it can able to access its own memory as well as this particular shared memory also. Likewise, process B also will attach to the shared memory by using a system call. So with that, now the process B can able to access the memory from its own plus the shared also. So that way here in this case, in case of shared memory method, where for declaring the memory segment to be shared and assigning to the or attached to this memory segments and all these things will be carried out, will be performed by the operating system calls, right? These three things. First one is that declaring the shared object or the shared segment, shared memory segment, and after that mapping the memory of each process with this shared memory object with the shared memory, and these things are done by the system calls. Once this is done, then afterwards coordinating these two processes by using the shared memory will be done by the at user level and all. It means that a process A want to access the contents of the shared memory, or a process B want to access that writing something, reading something, and how they coordinate. All these things will be carried out by the like the user program, by the user at a user level and user program and all, right? So that way, in case of a shared memory, the interference of operating system will be very less. Only at the time of like creating a shared memory segment and attaching to the shared memory segments, at that time only the operating system will come into the picture. That means the process will use the operating system calls to do that. So once that is done, then afterwards the remaining all other things like the coordinating of these two processes and accessing these contents of the shared memory. So all these things will be taken care by the user level process and all. Right? So that way, in case of shared memory, it will be faster, because once the shared memory is declared and attached to the corresponding process, then the data transfer or whatever the communication will be at the rate of memory speeds, at the rate of memory, just like normal accessing the memory content. So that way it will be very fast of accessing the data, accessing the contents, or the transferring of data or communication between the process and all. But initial system calls are required to initial setup, to make the memory region as a shared segment and attaching to that and all. So that requires system calls, and after that nothing is required. Yeah, this is about the shared memory idea. And here in the shared memory method, one problem is that because this is the memory that is shared by the multiple processes and all, and here while accessing this memory content, it should be careful, because there are multiple processes are allowed to allowed to access this particular shared memory. So therefore, you need to see that the contents that need to be contents that are there in the shared memory. So that should be consistent. It means that there should not be multiple processes right simultaneously. So all these things has to be very coordinated, and a kind of proper synchronization is required among the process to access the shared memory and all. So, but all these things will be taken care by will be handled by the at user level and all. So, but the problem here is that you have the shared variables and all these things are there. So therefore, a lot of kind of synchronization requirements and the coordination among the process. So those are required, and also sometimes the data may be inconsistent. If you are not able to take care about the synchronization properly, then whatever the data items that were there, so that may be the inconsistent. That may be that are accessed by the process that may not be consistent, and that may leads to the errors and all. So that is one of the problems with the shared memory. That means you need to handle the shared memory very carefully. by using appropriate shared variables and appropriate synchronization mechanisms and all. And whereas in case of the other one is the message passing scheme. In case of message passing scheme, the idea is here we have process A and process B. If they want to communicate, for example, then they make use of a kernel. They make use of the operating system to perform this job. So what it will do, so the process A want to communicate to process B, want to send a message to process B, for example, then whatever the message it want to send, it just passes the message to the kernel. That means the kernel may maintain some queue or whatever, or some kind of a buffer it maintains and all. So then the process A will pass the message to that particular queue or buffer, and then the kernel will see that there is some content in their buffer and all. Then it will see that who is required to where to pass and all. Then by knowing that it is designated for B, then it will inform to the process B, and the process B will access this particular message. So that way the process B will receive the desired message from the process A. So this is not to be message passing scheme. And here in case of message passing scheme, the kernel, like the usage of kernel or like intervention of kernel is more. It means that for sending the message to the kernel, it has to use the system call. And again, for receiving the message from a kernel, it has to use the system call and all. So therefore, for every message to be transmitted, it needs the system calls are required and all. For every message, you need to have a system call. You need to have a send system call by a sender, and a receive system call from the receiver is required and all. So that is required for every message. Whereas here in case of, so that way it may take more time. It needs more time also, because every time it needs the kernel support and all, because these are the two system calls, send and receive and all. So for every message, you need to have those both send and receive system calls are required. So therefore, the delay that is involved or the communication time that is required will be more compared to this memory, shared memory and all. Because in shared memory, in principle, once the initial setup is over, then afterwards simply the process A, because this shared memory segment is part of A and part of B also. So whatever it writes, it is also visible to B. It also can read and it can use it in its process and all. So that way, the kind of data transfer, or you can say that information transmission that happens between A and B will be at a rate of the memory speeds. Whereas here and all, it is based on for everything it has to do the system call, then the system call has to be executed. So that way the message passing scheme will be the delay. It needs more time to perform the message transmission and all. And the problem is that actually when you observe nowadays, actually using a shared memory versus the message passing and all, compared to the shared memory, the message passing seems to be more beneficial in case of multi-core systems like multi-processor systems and all. Because in case of multi-process systems, we have several cores are there, and when you use these the process communication through shared memory and all, so whatever the contents are there, it has to maintain the cache coherency across all the caches that are present in the memory. Suppose, for example, if you have like 8 octa-core system, for example, it means the system contains 8 cores. So each core contains the cache also. And suppose if you use the shared memory for process transmission, for process communication, so anything is changed in a particular cache and all, that has to be reflected across all the cache. So it's not to be cache coherency. And so it's a bit difficult, or it's more complex in case of the multi-process systems to maintain the cache coherency in case of this shared memory and all. So whereas here the message passing system and all, you don't have that. That means, but here a frequent kernel intervention is required. But in the analysis in the long run, when you analyze, the message passing scheme appears to be better compared to the shared memory in case of multi-processor environments and all. But in principle, it appears to be like a shared memory appears to be more very efficient in case with respect to the speed. But in case of multi-process systems and all, the analysis shows that the message passing seems to be beneficial compared to this one. Yeah. Um, then and now we are here. It's and now I just here we are discussing about the case of, for example, shared memory concept where the communication between the two processes using a shared memory. So here, this particular idea can be analyzed by using a standard a problem known to be a producer-consumer problem. So here it means that here the terminology producer-consumer problem means actually here producer is one process and consumer is another process. So it means that the producer will produce some items, and then the consumer is meant for consuming those items and all. That means the producer will send or will pass the information, and the consumer will receive that information. That's the basic idea. So here, in case of this on computers, where you will come across such relations very frequently at several places and all. Like for example, in case of a client server paradigm, where your web browser and web server, where you can say that the web server happens to be your the producer, and your the browser and the end users are happens to be your consumers and all, because you are requesting something and the browser will sorry, the web server will providing the desired pages or desired information to the browser, and then the browser will consume whatever the server is sending. And likewise, there are several occasions. For example, in the case of compiler, where the compiler happens to be producer, because the compiler will take the high-level language code and it compiles and it returns and it output the assembly language code, right? So in that case, the relation between the compiler and assembler will be like a kind of a producer and a consumer problem. Like means the compiler will derive the assembly code, will produce assembly code, and then the assembly code is again interpreted or will be used by the assembler to generate the objective code, right? And then these objective files or executable files, whatever, that will be again consumed by the loader. So in that case, the assembler becomes the producer, and the loader program is happens to be your consumer and all. So that way, in many instances, you can have the similar relations or the similar phenomena you can able to observe. So here in this context, we'll see that how these the shared memory will be coordinated between the producer consumers and all, between the producer and the consumer and all, right? So here in this case, actually here to have this one, the producer and consumer, so they are connected through a bounded buffer. It's nothing but some shared memory segment and all. It's nothing but a bounded. There are two unbounded buffer where there is no issue at all, because assuming that you have enough buffer is available, then there is no issue at all. That means the producer can able to produce the items, and he can able to push it into the buffer, because there is unbounded buffer. There is no limit for that. He need not check anything. Whenever the producer is ready with item, he can able to place it into the buffer and all. There is no constraint at all. But for the consumer and all, he has to check that whether the buffer contains any items or not. If the buffer is empty, then he has to wait for something. Otherwise, whatever the items are there, he can able to consume in a sequence, whichever the first it was produced that way. And but in the generic case, most of the cases, the buffers are bounded buffers. There are, that means finite buffers and all. So we'll see that how these producer consumers. That means there are two processes. At one end we have producer, other end we have the consumer and all. How they coordinate and all. Like it's very simple thing. There's nothing much. A very simple one. And here you can say that assuming that here just simplistic analysis, we are assuming that the buffer size equals to 10. That means it can able to hold 10 items. And this is the item nature structure. That means a structure, it has some attributes. That means item may have a record, and the record may have certain attributes and or something like that. This is the item type. And now the item with the item, we will declare that since the buffer equals to 10, so with the item, we will declare that there are 10 items can be hold. And then to coordinate the producer and consumer, we'll make use of these two variables, in and out. In and out, they are the two variables. And now, yeah, this is the generic thing to represent the buffer and other things. Then from the producer point of view, the code will be something like that. While true, it means that always whenever the producer is ready, then before placing the item to be in the buffer, the producer has to check this condition. The producer has to check this condition. That means in plus 1 modulo buffer size, if is equals to out, it means that now the buffer is full. It means that now because now we are viewing that buffer as a circular buffer and all. And then the in indicates that actually whenever the producer is ready with an item about to produce, and that the producer item has to be placed into buffer. And that produced item is placed into buffer indicated by the in pointer and all, indicated by the in variable in pointer. And then the out is nothing but, so whenever the consumer is ready to accept, ready to consume an item, so he will the item that is pointed by out will be consumed by the out buffer and all, by the consumer and all. So initially, when at the very initial point where we'll assume that both the in and out will point to the same location. That means both are point to 0. Both are point to the same location. And afterwards, whenever the producer will produce an item and all, then the in will be incremented, right? And then it will be incremented until the buffer is full. And likewise, whenever the consumer is consuming, then the out pointer will be the incremented and all. And for analyzing those two things and all, so here the in pointer has to be checked before placing the item into the buffer and all. You have to check this condition. Whether the in plus 1 this one modulo, whether it equals to buffer count, whether this modulo thing, whatever, if it is equal to the out, so it means that the buffer is full. There is no buffers at all. It means that the producer has to wait. Producer has to. That means it will keep on. You see that's the while loop and all. It keep on checks until the consumer consumes one of the items, so that you have some buffer is available. So that means if this condition met, it means that the buffer is full, then the producer has to wait. Producer has to wait, right? And then suppose if this condition doesn't met, it means that there is a room for an item to be placed. So therefore now wherever that means if this condition doesn't met, then you can say that in the buffer item in wherever is pointed, then the item will be loaded into that. Item is loaded into that. Then afterwards, then the in will be pointed to next. That means where the next item to be loaded and all. So that way, the producer side, you can use this particular logic. So with that, you can able to check whether the buffer is full or not. If the buffer is not full, then you load into the buffer and then increment the pointer likewise. And the same way that here the consumer side. The consumer side, the logic is that when the in equals to out, so this is the one where you have the empty condition. When the in equals to out at that time, that means there is nothing is there in the buffer and all, so therefore the consumer has to wait. That means he has to keep on wait. And then if this condition doesn't meet, it means that the in and out pointers, they are not pointing the same location. It means that the buffer is not empty. So therefore now whatever the buffer is there, whatever the item was there, whatever the item that is pointed by out, so that will be placed into the item, and then it will be taken out, and then out pointer will be moved to the next item and out. So out equals to out plus 1. So that way this in and out process, that means both the producer and consumer process, they will coordinate and then they will try to access the buffer while placing the items into buffer, or like the same time while consuming the items from the buffer and all. Yeah, here this is fine to some extent for coordinating the process and all. But there is a place where if both of them simultaneously want to access the system, want to access the program and want to access the shared region and all, so that time we need to take care about the synchronization of process for accessing the shared segments and all. So those things we'll discuss separately in the later part, where we have a process synchronization. An explicit chapter is there and all. So there you can able to discuss about how the shared segment will be accessed by the multiple users and all in detailed way. Yeah, this is an example of how this shared memory, how this IPC is carried out using a shared memory. And usually this IPC using a shared memory will be carried out by using an API, that is application programming interface. As we know that because for performing the shared memory or whatever, even for a message passing also, you need to access the system calls, right? So for that, use this. The API supports the application programming interface. This supports the library functions with which you can able to carry out the you can able to create a shared memory. You can able to access the contents of shared memory and all. And now here, this is a simple example code. I'm not going to discuss line by line. Just I want to mention what are the key points or key statements that are related to the shared memory creation and other things. Here anyway, the size, constant size 4096 bytes of shared memory may be required. That is why you defined here. And for accessing the shared memory, that shared memory will be, first of all, it is created as an object. It should have some name. So therefore, the name of the shared memory object will be given. Some name has to be given here, voice. And here, these are the contents that need to be passed to the shared memory, that need to be write into shared memory, that need to be read from the shared memory. So these are the two items, standard things, some strings, hello world kind of a thing. So here, what I'm just mentioning here, this is the size, and this is the name of the shared memory object. And then these are the strings that need to be passed into the shared memory, and then later it can be accessed and all. And so this is as I mentioned, the shared memory is also an object and all. It is a shared object, memory object. So therefore, it will be accessed by it can be a file descriptor like FD. And then for accessing the shared memory object, you have a pointer. So with that pointer, you can able to access the shared memory object in the memory. And then once for creating a shared memory object, so this is the system call that will be used, SHM open. And this name is nothing but the shared memory object, whatever the object name we have given. Here in this, we have given the OS as the shared memory object name we have given. And a zero create, it means that if that object is not there, then you create that object. And then these are the read write permissions to that object. And these are the directory permissions. So this way, this is basically a system call with which you can able to create a shared memory object and all. You can create a shared memory object. And after that, after create a shared memory object, and these are the permissions and other things. And then after creating a shared memory object, then you need to configure the size of the object. You need to configure the size of the shared memory object. So by using this particular system call, you can able to configure the size. Like, because the shared memory object is created and now it returns the file descriptor. It returns the file descriptor. And by using this file descriptor, you can able to configure the size of the shared memory, like whatever 4096, whatever. Then once the object is created, then afterwards you need to establish the memory map to the particular object and all, because that is a shared object. And whoever want to access that particular object, then you need to map the memory, because every process has a well-defined memory segment will be there. Now, if you want to access the shared memory object, now the shared memory object, whatever the address is there, that particular limits and all, that also will be now under the part of the address space of the desired the specific process and all. So this particular system call that is used to map this shared memory object to the particular process and all. So that way, this is a mmap, and then these are the file descriptor means the particular shared memory object which need to be mapped into its address space, right? And then it returns the pointer and all. This particular system call, finally, it maps the shared memory object to a specific process A, for example, and then returns the pointer. So once the pointer is returned, then by using this pointer, you can able to, the process A can able to write into the shared memory. And here for writing into the shared memory, these particular instructions are used as printf used to write the content into the shared memory. You can say that this is the pointer location, and from this location you need to write the message 0. So message 0 is nothing but hello, it seems to be, right? So then that hello will be stored, will be placed into the memory, into the shared object from this pointer location. And likewise, then afterwards the pointer has to be updated, because the hello contains 5 characters or 6 and all. So that based on the length of the message, then the pointer will be updated to load the next string. Here message 1, that has to be loaded again. So that way the pointer will be updated, and with that whatever the objects, whatever the contents you want to write into the memory, you can do that. This is simple, just a very naive example to illustrate how the shared memory object will be created, then how that is mapped to the address space of a given process and how you write into that. So this is from the writing part. Like the other one is that the same thing. Suppose that particular whatever is written by the process A that has to be consumed by the process B, for example, then he has to do the similar thing. He also has to mention the size and other things and all, and he has to open the shared object, everything, and he has to map the object here, right? And then afterwards he has to read from this. He has to display here the object is that whatever is there in the shared object that has to be displayed, for example. Then by using this you can able to do that. And after that you can unlink suppose for example the process, if they want to communicate and they adopt the, for example, shared memory concept, and then they can create a shared object, then they map to that, and once the communication is done, if that shared object is no more required, then by using this system call you can able to remove the, you can unlink from the shared object. So that way you can use the shared memory for like communicating the information between the processes. Okay. Yeah, don't worry about the entire thing and all. I've just highlighted that actually whichever the portions that are required, how the shared memory concept will be used for communicating the message, communicating the information, right? Yeah. So then yeah, the next thing is that, yeah, this is how the inter-process communication can be carried out using the shared memory concept. So the next, the other approach is that the message passing, because as you've seen that in case of shared memory, the idea is simpler. That means here the operating system will come into the picture only at the time of creating a shared memory object and mapping the shared memory, the object to the corresponding sender and the receiver, corresponding process and all. So once that is done, then afterwards the operating system is not at all involved in that. Then entire communication will be done directly between the process at the memory speeds, right? So the other, but the problem is that you need to have a proper synchronization is required, and proper coordination of the process are required, because that is done at a user side and all. You need to ensure that. So those things has to be taken care. Otherwise, because the data is shared by the multiple processes and all, and there is a chance of data inconsistency may happen. Suppose something, some process want to write something. So before writing itself, some other process may be using that. But actually, the process, the other process may have to use the item after writing this particular process. So sometimes it may not happen because of missynchronization and all. So therefore, you should have a proper synchronization of the process while accessing the data is very much essential in case of shared memory and all. And yeah, then whereas in case of passing, you don't have such constraints and all, because here there is no there is no memory segment that is shared by the multiple users. It's not there and all. Here, whatever you want to communicate, every time you have to use the operating system calls. So therefore, there won't be any problem of these constraints of like a coordination or synchronization. Those requirements are not at all required in case of message passing and all. Yeah, yeah, that's what here it is mentioning here. In case of message system, the process communicate with the other without restoring any shared variables and all. There's nothing is required here and all. Just simply a process whichever want to communicate. Then, yeah, again here also there is some delays are there. You need to first of all you need to establish the link. Then afterwards you need to do that. But here that kind of synchronization, those requirements are not there. So in case of IPC, that is inter-process communication, using this message passing, it will be carried out by using these two system calls, like the send message and receive message. These are the simple, these are the generic system calls was mentioned. And here, the depending upon the again message passing scheme, there is slight variation of these system calls will be observed later and all. And here again, while sending the messages, receiving the messages and all, again, there are issues are there, like whether those messages are fixed or variable size. And there are issues. If it is a fixed one, then it will be difficult for the user side always he has to constrain to pass the messages of fixed length and all, right? So that way it's not flexible. Suppose if you keep as a variable one, where from the user a process can free to send the segments of messages of the smaller or larger and all without any issue. But the problem is that the system level programming is difficult because if it is a variable size, again while sending and receiving the data by this primitives and all, then the system level you need to worry about that. You need to have more complex programming is required and all. So that way here the fixed and variable and all, if you keep it fixed it is flexible at one point of a time, and its variable means it is difficult at other place of. And then yeah, here if a process, for suppose P and Q, if they wish to communicate, so what is required? First of all, for communication between the two processes, first of all, you need to have some communication link has to be established first, right? And then through the link, by using these system calls, you can able to transmit the message and you can able to communicate. So again, so it means that in case of message passing, first of all, you should establish a communication link between the process, and afterwards through the communication link you can exchange the messages by using send and receive system calls, right? And then how do you implement this communication link? That means it has both physical and logical properties are there. It means physical means how the communication link has to be established, how it will be done, right? Using a shared memory or using a bus or using some network. Or logical properties means actually how this link will be, whether the link, what is the capacity of the link, what is the size of the messages that will tolerate, and what is the data rates and all, what is the bandwidth, and whether it will allow both the directions simultaneously or not. So these are the various logical properties about the communication link. So before attempting to the message passing scheme, we should be worried about how the communication link will be, what are its properties, what are its issues. So all these things will need to be discussed and need to be known about that while going for a specific scheme and all. Yeah, that's what I mentioned, how the links are established. Can the link be established between more than two processes and all? That means you have two processes P and Q are there. Is that only one link will be there, or like multiple links will be there? And how many links can there between a pair of communicative processes? That's what it means. And what is the capacity of the link, and what is the size of the message that can be accommodated, whether fixed or variable, whether the link is unidirectional or bidirectional. So all these things are related to the implementation issues, because you need to have a communication link between these two, and you should have this one. Okay, yeah, right. Now, I will stop at this point because you have a class test, right? So let me stop here. Okay, and your class test starts from 11:40, right? So you have enough time now. It's as per it's 11:32. You have 7-8 minutes time is there. No need to worry. And this test is 15 minutes. That means for 10 marks. And the actual time that is required is not more than 10 minutes. That 5 minutes is a buffer, right? So you please try to submit like immediately after 12-13 minutes and all, so that if there are any issues of network delays and all, that will be taken care, right? So because the most of the questions that I have given are also it's both multiple choice and the a short answers, and even the short answer also much simpler ones, right? So therefore it won't take much time, and you need to be stick to the time also. So the 15 minutes is only for the sake of the network delays and all. Don't assume that the 15 minutes is your time, right? So why I'm saying is that suppose if you drag on to the last minute, last few seconds and all, if you say that, sir, my network is a problem and other things, it's very difficult to accommodate in this scenario. So therefore, you assume that whatever the time that is given is not for your whole test time and all. It is for just taking care about this network delays and all. If your network is fast, then you can go till the last minute. We have no problem if you are confident on that. Otherwise, if you have a doubt on that, then you please try to wind up by just 2-3 minutes before the actual test itself, right? because it's not a uniform platform here. I cannot say that I will get, somebody may get 1 minute more or less because of your network speeds and your end systems and all. But the actual test requires 10 minutes. That's all. It will not take more than 10 minutes. So please use that and be in that, so that if you are in that, be in the teams, so that we'll announce the last 2 minutes and all. So the moment once I announce the last 2 minutes, you please try to wind up immediately within the 10 seconds. Then the things will be no problem at all. And there is no issue at all. Hardly like 1 or 2 issues I got the mail. Other than that, most of you are submitting within time. That is out of 229 response role list, I can see that all the time I can have like a 220, 215 responses were there successfully. So you please do that, right? I am now stop the recording first. Let me.